Hi, welcome to the webinar on scalable approach with 2x faster turnaround time for Arm Neoverse N2 design verification. This is going to be a joint presentation between Synopsys and Arm. My name is Satyapriya Acharya. I work as a senior manager application engineering in the verification group at Synopsys. I primarily work on the ARM-based or Amba-based subsystem and work on the Amba-based solution for ARM subsystem and ARM designs. Along with me, I have Eric Sonde. He is the senior product manager, SOC Development Solution Group at ARM. So together, Eric and I will cover this webinar where Eric will walk us through the different data center design challenges and introduce us to the Arm Neoverse solution. And after that, I will talk about the Synopsys verification solution to address the design verification challenges around those ARM-based Neoverse platform. Please send us your questions through chat window during or after the presentation, and we'll try to answer them at the end of the presentation. With this, I will pass it to you, Eric.
Thank you, Satya. I'm happy to be here today for this webinar with my colleague at Synopsys to present a hyperscaler system design and verification solution we have collaboratively developed. This solution enables our mutual customers to verify and validate ARM-based SOC architecture in the data center. Today, we'll start by sharing with you some of the trends we have observed in the data center to give you some context on why we developed this solution. We'll then briefly cover ARM's IP solution employed by SOC architects and hardware developers in this segment, and also dive into some of the design challenges that they are facing. I'll then briefly overview some of the ARM products that are key parts to the overall solution we provide to address the challenges described, and then I'll hand it back over to Satya to talk about this overarching verification solution in a bit more detail and describe the application of this methodology on a real-world use case for verifying the ARM-based server. There are three trends we have observed relating to compute in the data center. The first is a trend towards an ARM-based server. These are powerful, high-performance compute nodes for enterprise computing and cloud CPUs. The second trend is that these servers are being designed by cloud service providers, with a recent example being the 64-bit Neoverse core-powered Graviton2 custom-built by AWS for AWS. And we expect there will be many more examples to come in the future from several other cloud service providers designing with ARM. The third trend that we observe is that these cloud service providers are optimizing their server designs for their workloads, with cloud workloads requiring dedicated cores per thread and driving the core count higher for the server class SoC. ARM's Neoverse IP portfolio meets the challenges of the data center and more, enabling cloud-to-edge workloads. The Neoverse N2 is a highly scalable CPU that provides our partners latitude in attacking the cloud-to-edge spectrum. We see N2 addressing many problem spaces, from scale-out cloud down to edge compute. The N2 efficiency profile provides a lot of design freedom. Partners can build low core count, low frequency, power envelope optimized systems, and at the same time, they can take the same N2 core and build high core count, high frequency, large memory bandwidth monsters for the data center. And in the data center, we see the largest ARM-based servers, where N2 scales incredibly well, with an efficiency profile that allows partners to fit more threads per socket. Now, these Neoverse-based designs are enabled by ARM's system-level architecture and Amba, ARM's interface specifications and underlying protocols that connect all of the IPs in the system together. Here's a very brief overview of Amba. Amba is the standard for on-chip communications. It's an open standard, meaning it's developed collaboratively and it's freely available where anyone can use it. Amba defines the protocols and interfaces between different components in an SoC, but not the interconnect implementations themselves. It includes APB for simple and low bandwidth peripherals, as well as more mainstream specifications like AHB and AXI, and all the way up to CHI that defines the interfaces, or actually the architecture, for fully coherent, high-performance multi-core systems. And that's what we illustrate here, the different specifications and how they were introduced through the different Amba generations all the way to Amba 5, where we are today. Now, Amba is about having a common standard that scales and addresses a wide variety of requirements. But at the end of the day, it's really about our ecosystem. Amba has a really thriving ecosystem with partners from all across the industry collaborating and providing compatible IP, tools, and support, including the solution we are presenting today. Silicon partners have access to a comprehensive set of compatible and proven solutions, enabling design reuse and a low-friction integration, and ultimately lower risk, lower cost of ownership, and faster time to market, all of which enabled by the Amba specifications. Here's a view of the Amba interface revisions for CHI, ACE, and AXI, and how they map across the different CPU and interconnect IPs with our latest Neoverse N2, CMN 700, and NI 700 IP, taking advantage of our latest CHIE and AXI-H protocol revisions. The best practices for employing these many interfaces are exemplified in Arm's reference systems. Along with our Neoverse cores, we offer partners key resources needed to rapidly kick off designs. We are offering the Neoverse N2 reference design along with the CPU. In addition to providing architectural guidance and best practices at the system level, the Neoverse N2 reference design allows our partners to shift software development and boot an OS all on day one, and has a complementary fast model virtual platform. Now, starting from the N2 reference design, there are two key challenges architects face when designing for the data center. The first is scaling their SOC architecture for their workloads, and that requires workload modeling of the many CPUs in the system, along with assessing the behavior and performance of those workloads on the subsystem architecture, including the memory impacts and I/O subsystem latencies, as well as the effect of varying core counts on the coherent mesh interconnect. The second challenge is system-level validation across the highly complex blocks in the SOC, including protocol verification at each interface, assurance of compliance to standards like server-based system architecture, or SBSA, and performance validation of timing critical paths within the system. Now, at the heart of the design is Arm's SOC Coherent Mesh Network. The CMN IP and configuring and optimizing the central design element is the key for meeting these two design challenges. Arm's highly scalable, multi-chip optimized, PCIe Gen 5 ready coherent mesh network is at the heart of the Neoverse N2 reference design, enabling key features from Arm v9 architecture, including memory tagging extensions, tuning the highly configurable mesh topology and distributed system cache for this IP for the desired core count and workloads is a primary objective for the SOC architect. There are many parameters that define the highly scalable interconnect, capable of expanding to a 12 by 12 mesh topology, enabling up to 128 coherent clusters of Arm v8 or Arm v9 CPUs and accelerators, over 80 I/O nodes for over 160 AXI and ACE interfaces, and up to 40 dual channel memory controllers. There are also a number of microarchitectural features that can be defined to trade off power, performance, and area, including data width, coherency domains, SLC partitions, and more. For such a sophisticated and fundamental SOC component, hardware designers need a comprehensive solution to verify all of the interfaces at the periphery of the mesh topology and to validate the behavior and performance of the target configuration integrated into the system. At Arm, working closely with our EDA ecosystem and key partners like Synopsys, we aim to provide end-to-end SOC development solutions to enable our partners to build better, faster, and reduce design risk. Arm's SOC development products are provided directly and comprehensively to partners through our hardware success kits. The high-level design phases that our solutions cover typically take place linearly over time, starting with IP selection through the design and development of first silicon on through bring up and post-silicon performance optimization, with our most savvy partners and developers starting the software development cycle as early as possible so their software is ready on day one of first silicon availability. Our interconnect optimization solution is a case-in-point example where the architect starts by exploring ARM IP and SOC architecture, configuring the mesh with Socrates to not only configure the Neoverse CPU or other elements around the mesh, or to configure other IP from our comprehensive IP catalog, but to lay out the interconnect topology, specifying the microarchitecture, including caching system of the coherent mesh. They then continue on the design journey, exploring the performance of the interconnect using unit-level performance modeling capabilities integrated right into Socrates, quickly and easily visualizing the performance stats within the interconnect. Then, the hardware developers can intuitively bring up and debug simulations of the mesh with our Amba Viz analysis solution. Verification and system validation become simplified with protocol views and transaction-level debug capabilities for their emulation workflows. Now the tools provided by ARM are just a part of the equation to enabling world-class verification of ARM-based servers. Over to Satya for how our tools fit into the greater solution.
Thanks, Eric. So now I'm going to talk about the Synopsys verification solution for the ARM subsystem or Neoverse designs. So now let's look at the block diagram which Eric was showing for the Neoverse platform. If you look into this particular block diagram, you see that yes, the heart of the design is the CMN 700, which is sophisticated and complex. Along with that, you have multiple of N2, and then there are IO coherent masters or IO coherent generators which are sitting on top of the CMN 700 through NI 700. There are traffic coming from PCI to the CMN through the MMU, and then at the south you have the NIC 450 to connect to the peripherals, and you have the memory controller. Now this is one chiplet where basically you have one CMN 700 and you have the CXS interfaces through which you can connect other CMN 700 to the CXL ports, or basically a C6 interface. So what I'm trying to say that if you look into this particular architecture or the SOC, the scope of the verifications are many. You might need more than one test bench to verify the complete design. You might target to verify a specific IP. Say, for example, if you want to target to verify the CMN 700 or to verify the MMU or basically the CMN 700 and the N2s together. The scope of the verification can vary across the different requirements. And then as I was talking about different components which are attached to this design or the SOC, there are n number of interfaces which are connected to different interconnects, and the traffic is flowing across. Now, working with different customers, what we have seen, there are very specific challenges which our customers face today. Some of the key challenges which our customers are facing, I'm going to list it down. They are as following. So these are sophisticated interconnects, and it is critical to achieving latency and throughput goals. The SOC test benches representing multiple configurations with hundreds of interfaces are effort intensive and error prone. For such kind of a system, doing end-to-end data checking and coherency monitoring across a single CMN 700 or multiple of CMN 700 is going to be very complex. And on top of that, we have the very short project schedule which require early and cycle accurate functional and performance verification. To do that, you also need a simulator engine which can run or basically which do faster simulation. And on top of that, if you hit any issues during the simulation, you need a very smart and effective debugger to debug the simulation failures what you have seen. So again, looking back into this design and the design verification, there are very sophisticated challenges, and we are trying to provide a solution from Synopsys to address these challenges which our customers are facing today. Now, in this slide, I'm going back to where Eric has left that, okay, there's a Socrates from Arm, which basically used to architect and generate the RTL, which could have like multiple interfaces of Amba 5, CHI-B to CHI-E protocols, as well as AXI, A-Slide, and other interfaces, along with CXL and C6 interfaces. So the architects or the designer, they can use the Socrates to basically generate the RTL. Now, along with rendering the RTL or the Verilog code, this tool also provide an option to generate the IP exact for the design. Now, you can ask me what is an IP exact. So for the benefit of all, the IP exact is a standard defined by IEEE and Accelera, which basically is a language through which you can represent or define any circuit or any design or any block. So you can use the IP exact language to represent your SOC or your design. Now that way you get the design representation through the IP exact. From Synopsys, we have a tool called Auto Testbench, basically, which is used to generate test bench around any specific design. So basically, to provide or to generate a reusable and configurable and scalable test bench, we recommend or we basically provide the VC Auto Test Bench to basically provide or to create a scalable and reusable test bench. How it works? It reads the duty IP exact which gets generated by the Socrates tool. That way it understands the duty information. What I meant by duty information is the topology of the design, the different interfaces which are connected. And then from the Synopsys, we provide the verification IP, the Amba based verification IP and other interfaces IP. So this tool basically read the duty IP exact, and based on that, it basically selects the VIP using the VIP IP exact. The Synopsys verification IP has inbuilt VIP IP exact. So if it is an Amba interface, it picks up the Amba VIP. If it is a USB interface, it picks up the USB VIP. And if it is a memory interface such as DDR or LPDDR, it picks up a DDR or LPDDR VIP. So this tool basically reads the duty, reading the duty IP exact, picks up the VIP based on that, and then it generates a functional system Verilog UVM based test bench. Now I say that it will help you to create a highly configurable and scalable test bench. It does that by having a feature called passive and active RTL replacement. So what it does, as I said in the first slide, that to verify a reference design such as the Neoverse V2, you might have different verification scope. You want to only verify the CMN or maybe mix of CMN plus CPUs or maybe the entire SOC, right? For that, you do not want to build multiple test benches. Rather, you can build or generate a test bench using the VC Auto Test Bench tool, and that will provide you the options that at the compile time you can decide that which part of the design you want to verify. Do you want to only verify CMN 700, or you want to verify CMN 700 with the CPUs or with the NIC together? So this tool provides the active RTL replacement technology through which you can basically swap in and swap out RTL. What I meant by that is that you can replace a actual ARM CPU with a VIP, where the VIP drives the stimulus in active mode. And then when basically you move from CMN 700 to a subsystem where you pull in the ARM CPUs, then the VIP just sits as a passive to do the monitoring. So that is where this tool provides you a highly configurable and scalable test bench. So if you look at, this is how basically a test bench will get generated using the VC Auto Test Bench. So it will basically instantiate with the VIPs from Synopsys at every interfaces, basically depending on the scope where you want to instantiate the VIP. And then it it does the checking at every interfaces. So this is how a system or a test bench will get generated, and you have the control to define at the compile time that which portion of the block you want to verify. Do you want to verify only a specific IP or the entire SOC? Now, once this test bench is set, the next thing you want to do is basically to generate interesting traffic. So we provide a very scalable and basically a very scalable and comprehensive set of test cases and sequences for basically to do both protocol and system level verification. So we provide system level test suites as well as predefined sequences for the complete coherency verification. It provides the protocol specific transaction scenario as well as system level test cases to such as to check the connectivity, to generate traffic across the CPUs, across multiple chips to generate coherent and random traffic, along with to do basically the concurrency and the sequential traffic. So we provide a very comprehensive use cases test to exercise both system level scenarios as well as protocol scenarios to perform the functional verification. So next, that when you are running the stimulus, it's very important to also measure the verification goal, that how much percentage of verification you have achieved. So you need to track the progress of your verification. Now to track the progress of the verification, we provide something called as a verification plan, which are mapped to the functional requirements. So these verification plan are mapped to specification section, targeted application subplans, and then you have the configuration aware functional coverage model, which basically uh, tracks the scenario coverage for connectivity, application specific scenario coverage, and it has predefined transaction coverage. So overall, there are coverage model which are part of the verification IP, which will help you to track the progress of the verification, and then you can annotate the coverage result into the verification plan, and you get a very high level idea that what percentage of verification has been done, or you can track the basically track the progress of the verification. Now, what I've covered so far is that okay, that we provide a solution to generate the test bench, we provide the test suites and the scenarios or the sequences to generate the traffic, and then we provide the verification plan and the coverage model to basically track the progress of verification. Now, the next important thing is is basically how do you ensure that the traffic which is flowing across the the IPs or basically the design is accurate. Let's consider, as we mentioned, that okay, for a Neoverse kind of a design, the interconnect is the coherent interconnect, the CMN 700 is very critical. So to basically to ensure that the the coherency is maintained across the system or the coherency is maintained across the CMN, it is very important to perform those checks. So as part of a solution, we provide the CHI system monitors, which monitors across all the interfaces in the design. So it monitors across the Amba 5 CHI interfaces, the ACE Lite masters, the CHI slaves, the AXI4 slaves. It monitors across each and every port and ensures that the coherency is maintained in the system. Now this I was talking about a single CMN 700. Now let's consider that for the data center designs, there are designs which basically that there's not one, there will be multiple of CMN 700 which should be connected to each other. So there will be cascaded coherent interconnects connected to each other through the bridge gateway. And for these kind of design, the the monitoring becomes more difficult. So basically, the monitoring becomes more complex, and to have a, a, a very comprehensive checks to ensure again the coherency is maintained across different cascaded NOCs is very important. So here we provide basically the multi-chip system monitor as part of the solution, which checks and monitors the coherency across cascaded coherent interconnects. It does on-chip as well as off-chip coherency checking. So basically, within each agents, we have the protocol checks, which ensures that the the correctness of the protocol is maintained, and then we have the system monitors, which ensures that the system coherency is maintained. So basically, what you will see, you will actually see that for a cascaded coherent NOC kind of SOC, you need to have a multi-chip coherent system monitor which performs system level checks across the interconnect port. Now I'll just introduce you to some of the key checks which the system monitor perform. Some of the main categories of the checks which the system monitor perform are following. It checks the correctness of mapping between coherent transaction and Snoop transaction. It checks the correctness of sequencing between coherent and Snoop transaction. It ensures the data integrity between coherent transaction and Snoop transaction. It checks the coherency between master cache, data integrity across transaction data, the routing check, and many more. So these are only few which I have listed. There are many more which the system monitor perform. So this ensures that the data flow across the coherent interconnect and across the system is maintained, and the data is consistent across the system, and system monitor basically ensures that it is tracking that path. Now let's say while simulating you hit an issue, right? And then to debug these kind of scenario where maybe one of your coherent check is failing, and to debug that it basically need a very smart debugger. So that is where, as part of our solution, we provide Verdi protocol analyzer and memory protocol analyzer, where the protocol analyzer basically provide you protocol aware transaction and attributes over a GUI, where it synchronizes time, waveform, and the log file, and it link transactions to signal. So this basically helps you to quickly identify the source of the bug. It it basically gives you the insight into memory operations as well as into the cache operations. This is a tool which provides you flexibility to do interactive as well as post processing debug. Now to expand it, like let's say, as I said, the CHI is a layered protocol, and then the traffic across the interconnect is basically, it is difficult to track the traffic across the interconnect. Like I said, the CPU generating a coherent traffic, the interconnect possibly can send out a snoop or maybe can respond if depending on the snoop filter. Right now, it is important to associate the coherent transition to snoop transition, and something fails, it is very difficult to identify that okay, why something has failed, why the snoop which should have been generated by the interconnect is not getting generated. So that is where this protocol analyzer basically represent, or it associates the coherent transaction to the Snoop transaction, as well as it also associates the transactions level to the flit level. So it provides you very advanced level of search criteria. Say for example, like you want to put a search criteria, okay, I want to filter out all the cache line falling in address A to B, and starting from time t0 and ending with time t1. So that's the search criteria I put forward, and then the tool is going to filter out the the transaction which match the criteria which you have defined. So that gives you the information here, what I'm representing on the right hand side. It identify the overlapping transactions. It provides you the different transaction and the underneath flits, the request data and the response flit. And then it also gives you the coherent to Snoop association. And then from there, if you see that, okay, something has gone wrong, it's very easy for you to figure out, to visualize and figure out that, okay, something has gone wrong here. And if you need more from here, you can link the waveform, and also you can basically look from the simulation transcript to identify what has gone wrong. So this advanced debugger help you to identify the source of the bug very quickly. Now this so far I was talking about generating test bench and doing the functional verification. Now I'll switch and I will talk about the performance verification solution which we provide as part of our complete solution. So design like a Neoverse or the CMN, and then when you have CMN and other interconnects which are connected across them, the performance is very key. So for such kind of applications, uh, you definitely need to do the functional verification. On top of that, you also need to close on the performance verification. So to do the performance verification, we provide a solution called VCVIP Auto Performance, which uses the ARM Adaptive Traffic Profile specification. So ARM Adaptive Traffic Profile Specification basically provides a specification where you can define a set of attributes through which you want to generate a traffic. So basically, you define something as called a traffic profile. In the traffic profile, you define, okay, what kind of traffic you want to generate. That's going to be protocol agnostic and methodology agnostic. Okay. So that is the test profile or a traffic profile which the VCVIP auto performance reads in. You simulate it using VCS and then you analyze the result using the Verdi performance analyzer. Here the VCVIP auto performance generate Amba traffic to match the profile which you have defined. The Amba VIP has built-in traffic rate adapter and arbiter. So basically that reads the traffic profile and the test profile, and based on that, it converts into Amba specific traffic and drives it onto the DOT. Now let's look at one of the example of a sample traffic profile performance test. So if you see here, this is a sample traffic profile. Here I'm trying to list down few attributes based on which I want to generate a traffic. I want to generate a traffic of total number of bytes as 4096. I want to have a specific address starting from the base address with a sequential range. And then whatever I want to specify the ID or etc. I can specify here. So here I'm not talking about any specific protocol. I'm not talking about any specific methodology. So we are defining a traffic based on the traffic profile specification. These attributes are there in the specification, right? Now, if you want to control traffic across different masters, you basically can create a test profile which intermediate call the test profile, and then you map the path that, okay, how do you which traffic you want to run on which CPUs or which master agents or basically which VIPs. And then to synchronize between different initiators, right? The the specification talks about the synchronization logic. Here you can use the synchronization logic to generate traffic concurrently from multiple initiators or multiple RNF or multiple A slide masters. And also you can also generate traffic sequentially. So using the synchronization logic, you can define how do you want to generate traffic, either concurrently from multiple masters or multiple CHI interfaces, or basically sequentially doing a write followed by a read. You can also create a profile where basically you can just specify, okay, I want to generate a traffic of a rate maybe 1,000 megabit MB per s megabytes per second. And if I can provide that information, then the tool will take that as the information and then convert that into Amba traffic which to match the rate which you define and will drive traffic onto the DOT. Once you drive the traffic, you simulate it using the VIP and the VCS simulator, and then you analyze the result using Verdi Performance Analyzer. So once you simulate, it'll through VCS, it will generate a database called FSDB, which you can load it to the Performance Analyzer, and you can analyze the latency and the bandwidth, and if there are any violations. So the tool provides predefined metrics for latencies, bandwidth, byte count, etc. You can apply constraints to basically detect if there are any violation. You can trace the violations basically by natively synchronizing the protocol analyzer. So the performance analyzer and protocol analyzer, they are part of Verdi, and they use the native database called FSDB. So if you have applied a constraint for a latency, and let's say the latency number did not match, now the tool is going to report it as a violation. If you see here on the performance analyzer GUI, which is on the top on the AXI trans write latency, you see there are blue bars and there is a pink bar. The pink bar is the one which is basically is a violation. Now you can synchronize the performance analyzer window with the protocol analyzer window, and when you select on the violated transaction, the tool is going to trace it back, and on the protocol analyzer window it will highlight the transaction which has resulted in that violation. So that way, if you have any violations in the performance number, that such as in latency or in the bandwidth, then the protocol analyzer will help you to quickly identify that which transaction has resulted in that violation. You can export the performance reports and chats using HTML and CSV. This you can analyze in the GUI, Also, it supports batch mode. You can run a regression and get the result in a batch mode. As well as there are APIs available basically with this tool, which you can use in your test to generate or basically to dynamically control the traffic. You want to basically say, okay, you want to stop a test or abort a test if the latency numbers are not met. So you can build that in your test cases that okay, if the latency exceeds a certain number, you want to abort the test cases, right? Or if there are any violation, then the violation get reported in the simulation transcript. So those capabilities are all provided by the Verdi performance analyzer to analyze the result, and the VC order performance will help you to generate advanced performance-based traffic. And then to debugger, you can always use the protocol analyzer to identify the source of the bug. Now this I was talking about the system Verilog and UVM based test benches and the solution for simulation. Now let's transition it and how do you basically do a rapid transition from simulation to Zebu verification flow. So we provide synthesizable Amba CHI and ACE transactors and monitors for the emulation flow. Here we have over 10,000x faster interface over simulation IP using Zebu simulator. It basically provides seamless migration from simulation to hybrid to virtual emulation over unified VCS interface. Inherently, it provides non-blocking infrastructure, providing best transaction throughput, and it provides high-level abstraction via C++ APIs for faster software implementation. It gives you functional as well as performance monitoring. So what I've covered is basically we have a comprehensive solution for verification for the cache coherent SOC. We provide accelerated protocol verification using the Synopsys VIP and transactor, the automated test bench generation using VC auto test bench, the protocol compliance verification with Synopsys test suite, the system level monitoring with the system monitor, automated performance stimulus with the VC VIP auto performance, and functional performance verification with VCS. And then to achieve comprehensive debug, planning, coverage, power, and performance analysis, you can do it with Verdi. So to summarize, the goal here is to provide an automated verification solution to achieve 2x faster turnaround time for Arm Neoverse 2 design and other subsystems. So with this, I conclude the presentation and we move to the Q&A section. Okay, so I see there are a lot of questions on the chat window. I'm going to pick few. So first question to you, Eric. So there's a question like, which are the target applications for the Neoverse reference design? Is it data center, automobile, mobile SoC?
Yeah, great question. So as I covered in the talk, Arm Neoverse is really enables a broad line of products, enabling cloud-to-edge workloads. So the Neoverse N2 spans the broadest range from cloud data center and high core count, high power HPC, enterprise and cloud CPUs to the networking, enterprise networking and infrastructure edges, including switches and SmartNIC CPUs that trade off performance and power with more mid-core count. And then Neoverse N2 scales all the way down to low core count, low power gateway and router CPUs widely used in 5G infrastructure. So the whole cloud to edge spectrum and products along that spectrum can all benefit from the Neoverse N2 CPU and reference design.
Okay, thanks, Eric. So there's one more question after that. So what is SBSA standard compliance? Can you please elaborate a little bit on that?
Yes, SBSA stands for Server-Based System Architecture, and it's a hardware system architecture for servers based on 64-bit ARM processors that have various levels of compliance, from level 0 up to level 6. And these are really intended to drive an ecosystem for ARM-based server platforms and really seeks to strengthen that ecosystem by providing a set of features that the hardware can be compliant with, such that OSs can be easily built for a standard platform that complies to SBSA and will function correctly and be easy to verify without a lot of fine-tuning or modification.
Okay, thanks, Eric. So there's one question on the system monitor. Does the system monitor check coherency across CHI and IO coherent interfaces? So I'll take this question. So yes, the system monitor performs checks across the CHI and the ACE Lite as well as AXI IO coherent master. So we look into the system monitor, look at each and every interfaces around the CMN, and it checks the coherency across the CHI as well as the ACE Lite and AXI interfaces. The next question, can the system monitor do coherency checks when the actual CPUs are in place? Absolutely. The system monitor can perform checks irrespective of whether the VIPs are present in active mode or the CPUs are present. So when the CPUs are connected to the CMN 700, the VIPs can be configured or the agents can be configured as a passive agent, and the system monitor takes information from the passive agents or the passive monitors to perform the system level checks. So to answer your question, yes, Synopsys VIP can monitor when basically the actual CPUs are present, and the system monitor will do the end-to-end coherency checks across the CMN. Okay, the next question. Okay, the next question to you, Eric. What is the Amba Viz product you mentioned?
Oh, yeah, very good question. It's a relatively new product that allows intuitive analysis of system-level interfaces, so Amba interfaces, and coherent interconnects, as well as non-coherent interconnects, really aimed at providing system-level Amba functional and performance debug, providing some very intuitive debug views at the transaction level that look a lot more like the protocol specification diagrams and cover all of the Amba protocols, but especially the very complex CHI protocol and message passing interface, and provides a lot of very intuitive views for looking at how transactions fan out within the mesh, and how they might, one transaction or message might lead to several more, as well as some of the deep microarchitectural behaviors, including Snoop transactions and Snoop propagation within the mesh. There's also very good support for not just simulation, but emulation workflows to extract some of the waveforms from those simulations and emulations and post-process those and provide some of that protocol and IP level awareness that can provide some of these really intuitive debug views at transaction level. Amba Viz is included in the hardware success kit from Arm, so it's included along with all of the other tools for SOC development, like Socrates that Satya mentioned earlier.
Okay, thank you. So continuing on the debugger, so there's a question: can the debugger protocol analyzer associate protocol layer transaction and flits? Yes, as I mentioned in the slide, the protocol analyzer associate coherent transaction to Snoop transaction, as well as the coherent and Snoop transactions to the underneath flits, such as the request data and response flit. So basically, once you from the protocol analyzer, once you select on the coherent transaction, it will highlight the associated Snoop transactions, and then once you select either of the coherent or Snoop transaction, it will also highlight and give you the underneath different flits which are associated for that transaction. Okay, the next question is: can the performance analyzer provide latency and bandwidth information dynamically during the simulation? Yes, the performance analyzer provides API, as I mentioned in the presentation. You can use those APIs in your test to dynamically control the simulation. As I said, if you want basically your latency to be maybe a certain number. You do not want your simulation, or you do not want your test to proceed if the latency is maybe greater than 1000 ns. So you can put that, you can use the protocol analyzer APIs and put the check, and if the latency is basically violated, the simulation will report a UVM error. You can take a call whether to abort the transaction on that error or you want to continue with that. So this APIs can be also used to get a performance report in the simulation log between different initiators and targets. Okay, so I still see there are many questions. So because of the time constraint, we'll be not able to answer all the questions, but we are taking these questions and will respond to these questions over email. So with that, I would like to thank you all for attending this webinar and listening to us. Hope this session was useful to you. Goodbye and thank you.